Welcome to this video on Advanced Fluid Characterization and PVT Analysis, part of the Flow Assurance Expert curriculum. This module provides a foundational look at understanding reservoir fluids. Prepared by Dr. M. Fahed Qureshi, who specializes in the area of flow assurance, provides consultancy, and also has published several works in this area. Feel free to reach him out. In this first section, we will cover the fundamentals, specifically focusing on the essential building blocks of reservoir fluids and their role in flow assurance. Why does PVT matter? Accurate data is the foundation of modeling and is critical for predicting operational behavior, helping prevent costly subsea line blockages caused by waxes, asphaltenes, or hydrates. Reservoir fluids are generally classified into 5 types, ranging from black oil to dry gas. This classification depends on the initial reservoir temperature relative to its critical point and the phase envelope. The cost of inaccuracy can be high. Even a 10% error in PVT characterization can lead to massive miscalculations in subsea thermal and hydraulic designs, potentially resulting in billions in deferred production. Proper fluid sampling is the first step in analysis. Capturing representative fluid at downhole conditions is vital, as the sampling method determines the accuracy of all subsequent compositional data. Downhole fluid analysis, or DFA, allows for real-time measurements directly in the wellbore, including optical spectrometry, density and viscosity sensing, flowline pumping, and dynamic gradient mapping. To ensure data quality, we follow strict sampling criteria. This includes verifying opening pressures, monitoring mud filtrate contamination levels, and ensuring mass balance during recombination. Moving to Section 2, we will explore compositional analysis, covering the journey from gas chromatography to managing plus fractions. Gas chromatography is used to separate hydrocarbon mixtures into individual components based on their boiling points. This process provides a chemical fingerprint essential for identifying flow assurance risks. A core principle in reservoir engineering is that the overall phase behavior of a fluid is largely dictated by its heaviest and often least defined components. Characterizing these heavy plus fractions typically involves 3 steps: extrapolation to estimate properties, splitting into carbon number groups for modeling, and lumping to optimize simulation speed. In a typical volatile oil, the C13 plus fraction might be small by mole percent, but it exerts a dominant impact on phase boundaries and the risk of liquid dropout in subsea lines. Section 3 covers laboratory experiments. These experiments are essential for generating the high-quality, ground truth data required for accurate equation of state tuning. The constant composition expansion, or CCE test, is a primary laboratory method. It establishes the baseline phase envelope by determining saturation pressures and fluid volume changes as a function of pressure. Depletion tests are vital for understanding reservoir performance. Differential vaporization, or DVT, simulates black oil depletion, while constant volume depletion, or CVD, is used for gas condensate reservoirs. Multi-stage separator tests help optimize surface facilities by understanding fluid behavior at different pressures and temperatures, providing critical data like API gravity and formation volume factors. Specialized flow assurance tests address operational risks. These include measuring wax appearance temperature, detecting asphaltene onset pressure, and determining hydrate equilibrium points. We now move to Section IV, focusing on equations of state, the essential mathematical engines that drive flow assurance modeling. The evolution of EOS models has progressed from simple ideal gas laws to cubic models like Peng-Robinson, and finally to advanced models like PC-SAFT for complex chemical inhibitors and asphaltenes. The Peng-Robinson equation of state remains the industry standard. It relies on critical pressure, critical temperature, and the acentric factor to accurately predict vapor-liquid equilibrium. This slide displays the general cubic form of the Peng-Robinson model, highlighting how intermolecular attraction and molecular volume are mathematically represented. Accurate simulations require solving for phase stability and flash calculations, utilizing algorithms like tangent plane distance and the Rachford-Rice equation to predict phase composition and fractions. In Section V, we look at EOS tuning and regression, a critical process for aligning theoretical mathematical models with experimental laboratory data. Tuning is an exercise in bounded regression. We must never sacrifice physical reality just to achieve a better statistical fit during the regression process. The tuning workflow involves 3 main stages: inputting and cleaning laboratory data, processing fractions, and finally performing regressions to match target results. Best practices for regression include starting with heavy pseudo-component properties, maintaining monotonicity, and using volume shifts specifically for density corrections. A well-structured regression strategy is essential. Avoid over-parameterizing the model, which can lead to curve fitting and unphysical results that compromise reliability. Once tuned, your model is exported to flow simulators like OLGA or LidaFlow. This file essentially dictates safety margins, chemical injection rates, and operational envelopes for subsea production. That concludes our first module on advanced fluid characterization. Please review the material before we move on to the next module on multiphase flow hydrodynamics. Thank you for watching this presentation. If you are interested in consulting, research, or professional technical training, please feel free to reach out via the contact information provided in this video.